Hi everyone, I believe I'm live right now. Start thing. Let me quickly verify if I can hear myself. Uh, okay, I think you guys can hear me. All right. Yes. Welcome to another lecture. So today we'll be solving two problems, and I'll be giving you a few more problems for your homework. But before that, for in the last class, I've given a few problems for homework. I'm not sure if you guys have done that or not, but again, I'll not discuss the solutions completely, but maybe in case if you guys got stuck somewhere, I can help you around that. So let me know if you guys have solved. So these there were three problems. One of them was uh, it was detecting loop in a linked list, which is same as Freud cycle detection. We had already done that in the last class, so I'm not taking that up again. But other than that, these were the two problems: finding the nth node from the end of the linked list, and it's pretty easy problem. And the second one is intersection point of Y-shaped linked list, right? So you are given these two questions. Let me know if you guys have solved these both of these questions. Do you have any doubts on these, or do you have any problem with these? Let me know about that. Okay. Oh, I have to change this to dark mode. Let me just change everywhere. Cool. That makes- Yep. Have you guys gone through the questions? Have you guys solved it? You are not able to solve. Let me know if you had any problems. How did you solve this? Anyone? How did you solve intersection point of Y-shaped linked list? Anyone would like to volunteer here? How did you solve it? Okay, I think we're live back. I had some internet issue. Sorry about that. Okay. Took length. I coded up unable to write optimal code. Took length difference. Okay, timed out. Then I took help. Okay. So how would you solve this? Just like I'll give you a hint. I'll not solve this problem explicitly. But how would you actually solve this? I think Muhammad, you are pretty close to it. You do have to take the difference of the lengths. So I think you can. What you can do is you can first run two loops, one loop for finding the length of the first linked list, second loop for the second linked list. Once you have found the difference of the length in the first linked list, like in the bigger linked list, what is it? Like if its length is more, it means that it has more number of it has to travel more, right? Like let's just think about this. What does length more mean here, right? So if there are two linked list, yeah, definitely you can do using hashing as well. That's another way, but again, like this is also one way, right? So let's say this length is more, right? And there is another linked list whose length is less, so let's call it L2, let's call it L1, right? So the length of L2 is less than L1, so these many by these many. So what you should do ideally is, you first of all, you have to come to the same level, right? You have to come to the same level for both of them. So you first travel this distance d, which is the length 1 minus length 2. You travel that much distance. Now you have two pointers at the end of both the linked list, right? At some point, right? Now you can go one step at a time until you reach this point, and you will reach this point like for both of them at the same time. So let's say you go here, you go here, then you go here, you go here, then you come here, you come here, and finally you meet here for both of them. So you can just run one loop again, and that will be a order of n solution, right? That will be order of n solution. What Dashun suggested is also actually true. You can, instead of actually like running three loops, what you can do is you can maintain a hash map of the nodes that are available in one of the paths, right? So just take one of the linked list and maintain a hash map of the nodes available in one of in it. And for the second linked list, when you travel, you check whether that node is available, right? So the first node that matches with something in the hash table, or that is present in the hash table, that is actually the first intersection point, right? So you can do in both the ways. But yeah, like that's mostly the solution. I'm not going to write the code for that. It's up to you. You have to try writing the code for this on your end, right? So but again, that's the solution. So I believe that you should be like, once you go home today, you should be able to solve this problem. So let's end this. And also this is also like pretty simple. Init node from the end of the linked list, it's pretty simple, right? You if you know the init node from the end, you know the length of the linked list. So what is the position from the beginning of the linked list? That is L minus n, right? So L minus n, you have to travel a distance of L minus n in a linked list. So that's pretty simple as well. So we'll not look into this as well. Okay, I believe like that should be good enough. So let's start with today's questions. Okay, and again, like today's questions are available on the description along with the practice problems. So make sure that you check the description out. You get the practice problems, you get the problems we'll discussing today, and make sure you have them, right? So first question that we'll discuss today is what is the left view of a binary tree, right? Left view of a binary tree. What does that mean? It means that you are given a binary tree, you have to print the left view of it. What is the left view? Left view of a binary tree is the set of nodes visible when the tree is visited from the left side. So just think that you are given a binary tree in front of you, right? So you are given a binary tree like this, and you are watching from the left side, you are watching from this side. What is the set of nodes that you can see? That is the left view of the binary tree, right? So for example, in this tree, if you are watching it from the left side, what is the set of nodes that you will see? You will see 1, 2, 4, and 8, right? So 1, 2, 4, 8 is the left view of the binary tree. Now again, like similarly, 1, 2, 3, 1, 3 will be the left view of a binary tree. So I'm pretty sure that you have some ideas here, but I believe that many of you will actually be wrong here. So can anyone tell what would be a easy way to solve this? Or if you have some ideas, can you tell like what can you do here? I believe the question is clear. Like you have a binary tree given to you. Let's draw a binary tree. Here canvas is happening. So 1, 2, 3, 4, 5, 6. So in this case, what you do is you are watching. Just assume that you are standing here, right? You are standing here and you are seeing the tree from this side. So you are seeing the tree from this side. What is the set of nodes that you can see? You can see 1, you can see 2, you can see 4, you can see 6. You cannot see 5 because 5 is blocked by 4, right? 5 is blocked by 4. So you will see 4 only. You cannot see 3 because 3 is blocked by 2. So you can only see these set of nodes 1, 2, 4, 6, right? So we can use level order traversal. Why level order traversal? Why not depth first DFS? Can you tell why are you using level order traversal? Okay, I'll ask a easier question. What if, will this work? Will this work if I just travel on the left hand side? If I do a DFS on the left hand side, because only the elements on the left hand side can be seen, right? So if I just go to the left hand side always, won't I get the left view of the binary tree? Can you tell? Won't I get the left view of the binary tree if I just DFS on the left hand side? If I just DFS on this left hand side, won't I get the left view? It will not work. Why will it not work? Why will it not work? Or if it will work, you can also tell anyone, will it work or not? Uh, that's fine, right? We have a leaf node here as well. That's okay, right? These are all leaf nodes. Still, the answer will be 1, 2, 3, 4, right? Let's say 1, 2, 3, 4. The answer will be the same. Okay, I'll actually explain why this will not work. Let's take an example, right? I understand what you're trying to say, but I agree that it's difficult to type in as well. So let's understand what actually the problem is here, right? So let's say we have a tree like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. What is the left view now? What is the left view now? If you look from the left hand side, just see. If you look from the left hand side, you can see 1, you can see 2, you can see 3, you can see 5 after that, right? You can see 5 after that because 5 is not blocked by anything on the left. So you can see 5 after that, and after that you can see 9 as well. So if you see, it is not always in the left subtree that you are searching into, right? You are looking into nodes that are not blocked. So that's why if you just go to the left hand side, right? Yes, exactly. If you just go to the left hand side, it will not work. I hope it makes sense that. So the solution for this, it's pretty simple actually. Like, I think you've already got the idea. At any level, we can only see the first node. At any level, we can only see the first node. For level 1, you can just see this node. For level 2, you can just see 2. For level 3, you can just see 3. For level 4, you can just see 5. You cannot see 8. For level 5, you can just see 9. So at any level, we can just see the first node. So that's the logic. You just have to maintain the first node at every level. So when you are talking about levels, level order traversal comes into our mind, right? So we will do a level order traversal on this tree. We'll do a level order traversal and we'll maintain what is the first node that we see at every level, right? At every level, what is the first node that we see? And that will be our answer. Make sense? Does it make sense with everyone? Or anyone has any doubts with this? Let me know. Right. Does it make sense to everyone? Got it. No worries. It's okay. Like, you can learn today itself, like what BFS is. So what we do in BFS, basically, we'll go over level by level, right? We'll go in first level, then we'll go to the second level, then we'll go into the third level, then we go into the fourth level, then we go into the fifth level. Like that, will go one by one, and that is possible using a queue, right? That is possible using a queue. Just imagine that you have a queue, right? You have a queue, so you enter 1. From 1 you get 2 and 6, so you enter 2 and 6. What is a queue? A queue is a first in first out, right? So this was entered first, so 2 will be pulled out first, then 6 will be pulled out, and on top of 6, 3, 4, 7 will come up. So it will be going in a level by level fashion. So that's a BFS, right? So we'll look into the code right now. So I think that will make more sense. So let's jump to the code. Okay, so let's go to full screen now. We want to maintain the leaf view, right? So first of all, we'll maintain a vector of the left vector of the view, and it will be of size. What will be the size? The height of the tree, we don't know that, right? We don't know the height of the tree, and initially everything will be -1, but we don't even have the height of the tree, right? So maybe we can write a utility function that will return the height of the tree, so that we can maintain a -1, I believe. But that's fine actually. Let's not do that. We can do it in a different way as well. So view, this will store the left view of the binary tree, right? Now when we go for a level order traversal, what do we use? We use a queue. So we'll use a queue here, queue int x, right? So x dot, I think push and pop are the methods. So x dot push root of root, x dot push root, and it should be node start because we are pushing nodes, right? Root, and view dot push back root of data, right? So int current height. So also we have to maintain what is the current height that we are looking into. So for that, let's just not push a node start, but what we can do is we can push a pair, right? Pair node start. Pair means we'll push two values. One, the first value is the node, the pointer to the node. The second value is the height, the corresponding height or the depth of the node, right? That has been pushed. So root is at depth 0. So root is at depth 0. So root will be at depth 0. Or let's call it 1, right? So that we can have the size in place as well. So root is at depth 1. So the next nodes will be at depth 2. The next node will be at depth 3, and like that it will go on, right? So current depth we are considering, we don't have to maintain that as well, right? Now while not x dot empty, while x is not empty, right? So pair node star and int tp equals to x dot front and x dot pop. We'll remove the first node, and we'll do that. Okay, now we will see if tp dot second, if tp dot second is greater than, if the depth is greater than the size of the view that we have, that means it is the first node at that depth, right? It is the first node at that depth. So view dot size, for example, when the first node is removed, what do we have? We have the depth to be 1, right? So it will be 1. Is 1 greater than view dot size? View dot size is already 1, right? So it is not greater. So, or we can remove it here as well. We can directly push here. So right now then it will be greater, so it will come into this loop, and view dot pushback tp of first, tp dot first of data will push the data here, right? Now we will see if, so let's take the node out, right? Let's take the node out as well here, so that it makes the code cleaner. Node star current node star current equals to tp dot first. So I think this will make the code much cleaner. So we are considering current, we'll push current of data, right? Now we'll go into the left subtree and the right subtree. So if current of left not equals to null, in that case what do? We'll push it. So x dot push current of left and tp dot second plus 1, height depth plus 1, right? Depth plus 1. I'll do a dry run for this, don't worry, in case it's not clear. I'll do a dry run for this. If current of right, so we'll go to the right child right now. So not equals to null, in that case x dot push, what will we push? Current of right and tp dot second plus 1 again, right? And we are done with this, right? We are done. Finally we'll return view. So that should be the code. Let's compile and run this and see if it is working. Okay, it's working for now. Let's assume that it will work and submit it. Okay, I think it should work. It's going into a segmentation fault. Can the, one second, can the tree be null or something? Oh, number of nodes can be 0, right? So number of nodes can be 0, so in that case we should return empty. So if root equals to null, in that case just return a simple empty vector. So vector int. I think that should be it. Okay, it's done. So I'll quickly dry run through whatever I've done, right? So the code, just look into the code once. I'll see if I can actually snip here. What does this do? I think, yes, I can do it here, I believe. Okay, so see what I'm doing here. Let's consider a tree here, right? Let's consider a tree here. So let's consider the tree like 1, 2, 3, and 4, 5, 6. This one, right? Let's consider this tree 1, 2, 3, 4, 5, 6. What are we doing? See, first of all, we are pushing root and 1. So root we are pushing. So this is the queue. Let's assume that this is the queue that we have. on the top we are having this q. First of all, we are pushing root, that is 1, and its height as well, that is 1 depth, right? Now our second array, which is the views array, this is empty initially. Views array is empty, so this is the views array. Okay, now we come here, x dot pop. What is at the top of the queue? Only one element is there, this one, so that is popped, right? That is popped, so that is popped from here. What do we have? We have 1 1. We have 1 1, right? We have 1 1. Okay, now we see tp dot second. What is tp dot second? It is the depth. It is the depth. If it is greater than views dot size, that means we don't have a node for that depth. We haven't inserted, or this is the first node for that depth, right? So right now views dot size is what? 0. What is tp dot second? It is 1. So 1 is definitely greater than 0. So we'll push back current of data. Current of data is 1. 1 is the data, right? So 1 is pushed into this queue, into this views array, right? After that we go to current of left is not null, so we'll push 2. And what is the depth of 2? It is whatever is the depth of 1 plus 1. So tp dot second plus 1. So tp dot second is 1. 1 plus 1, 2. So the depth of, if the depth of 1 is 1, the depth of 2 will be 2. The depth of 3 will be 2. The depth of 4 will be 3. 5 will be 3. 6 will be 4. Right? So like this, we will have the depth. Okay. Now, similarly, 3 is also pushed. So 3 is also pushed with the depth of 2. Right? Now we again come back. It is not empty. So we'll remove the front element, which is 2. We'll remove 2. Now, we remove 2. When we remove 2, what do we have? We have 2 comma 2, right? What is the second element? What is the depth? Current depth we are considering. The current depth is 2. What is the size of views array? Size of views array is 1. So 2 is greater than 1. That means we do not have a node or at depth 2 right now. And this is the first node that is coming at depth 2. So that means we'll insert 2 into the views array. After that, we'll go to current left and current right. So both of them are null. So nothing is inserted. Now will be the interesting part. Now we come back again. This is not empty. So 3 2 is brought out. 3 2 is brought out. 3 2. Okay. Now we go into this check, right? What is the check? tp dot second. What is tp dot second? What is the current depth of 3? It is 2. What is the size of the views array? The size of the views array is also 2. That means for the depth of 2, we have already found a node which is on the left hand side of 3. We have already found the first node at the depth of 2. So it is not greater. It is equals to, right? So will not push it into the views. Now we'll go to left and right, and both of them are there. So 4 is inserted with the depth of what? tp dot second. tp dot second is 2 plus 1, that is 3. So the depth of 4 is 3, and 5 is also inserted with the depth of 3. Right? Now we pull 4 out. At the front we have 4. At the front we have 4, so we pull 4 out. Right? 4 3. What is that current depth? Current depth is 3. What is the size of the views array? 2. That means for the depth of 3, we haven't found a node yet. Or this is the first node at the depth of 3, which is 4. So we will add 4 to this views array. Now, we don't have left and right, so these will not be pushed anything. Now this is removed from the queue. Now 5 3 comes in. 5 3 comes in. What is the depth of 5? 3. What is the size of the views array? 3. That means we already have found a node at the depth of 3, which occurs in the left hand side of 5. Or we have already found the first node in the depth of 3. So we will not be able to see 5 anymore. So we will not insert it into the views array. Now it has current of left, so 6 4 is inserted. Right? 6 4. Why 4? Because depth of 5 is 3. Depth of 6 will be 3 plus 1, that is 4. Right? 3 plus 1, that is 4. Okay. 6 4 is inserted. Now we pull 6 4 out. Only one element is remaining. We pull it out. 6 4 is pulled out. What is the size of the views array? 3. What is the current depth of this node? 4. So that means for the depth of 4, we haven't found a leftmost node yet, or this is the leftmost node. So we'll add 6 to the views array, right? So like this, we get the views array to be 1, 2, 4, 6. And it is indeed 1, 2, 4, 6, right? 1, 2, 4, and 6. So that's why this is 1, 2, 4, 6. Does it make sense? Does it make sense? Let me know in the chat. Is the code making sense how I have done this? Does it make sense? Okay, awesome. Let me know if you have any problem with this. Okay. So this is the first problem. Wondering about right view. Just think about it. How would you do the right view? Right view is just the opposite, right? So if you visit the right node first and after that the left node, doesn't it give you the right view? Just think about it. Yes, I maintained the levels vector. Yes. Doesn't it give you the right view? Just think about it. Let me draw something. 1, 2, 3, 4, 5, 6. Right. So if I first inserted 3, so then I first visit the right hand side, then the left hand side. So what would I get? First 1, then 3, then 5, then 6, right? So I get the right view like this. Cool. Awesome. So let's go to the diameter. So the second, this is also a very easy problem. It is the diameter of a binary tree. Now, what is the diameter of a binary tree? It is the, or diameter of any tree, right? It is the largest distance between two nodes of a tree, right? By the way, my name is not Soham. It's written wrong in the description. My name is Soham, Soham, not Sohum, right? So the spelling is something Soham, Soham, not you. The team has messed up there somewhere, but yeah. So the diameter of a tree, sometimes called the width, is the number of nodes on the longest path between two end nodes, right? So the diameter of a tree is the number of nodes on the longest path between two nodes. So you have two nodes. What is the maximum distance between two nodes? It is the diameter of a tree. The diagram below shows two trees with a diameter 9, the leaves from the end in each path, right? So basically, this is the diameter of a tree, right? This is the diameter of a tree. Like in this example, if you see, what is the maximum distance between two nodes? Now we are definitely sure that the maximum distance between two nodes will be definitely, those two nodes must be the leaf nodes. Those two nodes must be leaf nodes, right? Because otherwise we can always go downwards to a leaf node and increase the distance, right? So the maximum distance is always between two leaf nodes, that we are sure of. Coming to the second part, if you see, in the first case, max distance between the right and left node, that's actually false. That's actually false. You can see in this example only. In this example only, the maximum distance between the rightmost leftmost node is 1, 2, 3, 4. Rightmost node is 1, 2. So 1, 2, 3, 4, 5, 6. The diameter is 6. No, it is not 6. You will instead get a diameter better like this. If you see around this path, 1, 2, 3, 4, 5, 6, 7, 8, 9. You are getting a diameter of 9. So it is not necessary that it should always pass through the root node, but it will be two leaf nodes for sure, right? It will be two leaf nodes for sure, but it is not necessary to be passing from the root node. And this example actually shows that the first example actually passes through the root node, but the second one we see that it doesn't pass through the root node. It passes through an intermediate node, and then goes, right? It will go through this node, it will go downwards, right? So you have to find the maximum distance between two nodes. Now we are sure that the two nodes will be leaf nodes, right? The two nodes will be leaf nodes. So how do we do this? It's pretty simple actually. And if you see, the complexity is order of n and the space complexity is order of height of tree, which is because when you do a DFS, it takes a order of height of tree, right? DFS or BFS. So let's understand how can we do this. So what do we know about a leaf node? Let's say it is any arbitrary node, right? This is any arbitrary node. Let's call it A. Let's say the diameter passes through A. The diameter basically diverges from A. That is, there are two nodes, somewhere here B and somewhere here C. From B you come up to A and then you diverge towards C, right? So basically for every node, if we can calculate what is the maximum diameter or what is the maximum distance between two leaf nodes in the two subtrees, that is, we are sure that if it diverges from A, then B will be in the left subtree, C will be in the right subtree. If it diverges, otherwise how will it diverge from A, right? So there are only two nodes, two child nodes for a node. So if the diameter or if a maximum distance diverges from A, then B is from the left subtree, C is on the right subtree of A, right? So with this, what we can do is, for any node, for every node we'll calculate this. What is the max? This is the left subtree, this is the right subtree. What we want here is the max distance leaf node from A. Max distance leaf node from A. And here also we want the max distance leaf node from A. Right. Let's say this is B. Let's say this is B. Max distance leaf node from A on the left subtree is B. On the right subtree is C. So that means the maximum distance of two nodes that are passing through A, maximum distance of two nodes whose path is passing through A, or whose path diverges through A, will be the distance of B plus the distance of C. It will be distance of B plus distance of C plus 1. 1 for A, right? So it will be distance of B from A plus distance of C plus 1, right? So like this, for every node, if we find what is the maximum distance of two leaf nodes that are diverging through this node, then our diameter definitely diverges through one of the nodes. So the maximum of all possible values will be the answer. The maximum for all possible values will be the answer. And in fact, this is the same way we can find the diameter of a n-ary tree. For n-ary tree, we don't have two child nodes, right? So for n-ary tree, it becomes a bit complicated here. What we have to do is, we have a node A. If we want to find the maximum distance of any two nodes, we go through all the subtrees, right? We look at their maximum distance nodes. Let's call it B, C, D, E. We take the first and the second maximum of them. B, C, D, E, whatever they are the maximum distant nodes in the corresponding subtrees of the child nodes, we take the first and the second maximum of them, and that is the maximum distance to nodes that diverges through A. So we use the same logic for n-ary tree as well, right? So the code for this will be very simple. Let me know if you have any problem with the logic. So the code will be pretty simple here. I think I've chosen what? Right. So let's maintain our answer variable here, int answer. And also we'll maintain a helper function here. Max height, or max height, right? Max height. So we'll find the we are given a root node. We'll find the max height leaf node, or max depth or max height, same thing. Max height leaf node, right? we'll find the max height leaf node. So if root equals to null, if root is equals to null, we'll just return 0 because there is no leaf node. Otherwise, we'll find the left max. Left max equals to max height leaf node. We'll basically do a DFS here. So we'll go to the left subtree and find the left max. We'll find the right max equals to max height leaf node root of right. Now this method should return what? It should return the max height of leaf node from the current node in the subtree of the current node. So what will be the max height of the leaf node from the subtree? It will be the maximum of the left max, right max plus 1 because this node is also included. So the height or the depth increases by plus 1. Now we have this. We also want to compute the answer. What will be the answer? The answer will be max of answer left max. We go to the left side. From the left child we come to this node, then we go to the right max leaf node. So right max plus 1 because the current node is also visited, so plus 1. So that will be the answer, and we'll find the maximum over all possible nodes, like all possible nodes where it can diverge. So this will be the answer, right? So first we'll set the answer to be equals to 0, then we will just call max height leaf node and pass the root, and then we'll return answer. Simple. So if we compile and run this up, let's see. Yes, let's submit. Okay, it will pass basically. So anyone has any doubts with the logic? I think it is pretty intuitive, like it's pretty simple as well. So first observation is that it's not always passes through the root. Like it's a common mistake that you can make that you go to the leftmost node and the rightmost node, but it might not pass through the root because you can take an example from here. So if you go through this example, actually let's just go through this example. So if you go through this example, that basically if you see the path, it comes from here like this, it doesn't go to the root, then it diverges away from here, right? So what we do is for every node we'll compute what is the maximum leaf nodes, right? Maximum distance of leaf node. So we'll find the maximum distance of leaf node on the left subtree, on the right subtree. Now on the left subtree, let's say so just let's come to this node, right? For this node let's call this A. What is the maximum distance of leaf node in the left subtree? Let's see the left subtree. So let's consider depth is 0 1 2 3 2 3 4 5. It has depth 5, it has depth 5, right? These are the leaf nodes. On the right side, 1 0 1 2 3 4 5, right? 5. So yeah, 5 5, but again, like we are computing from the top of the node, so we should compute from the in a subtree level. So from a subtree level, it's 1 2 1 2 3 4 4 1 2 3 3 4 4, right? So what is the maximum distance of a leaf node in the left subtree for this node? What is the maximum distance in the left subtree? For left subtree, we have 3 leaf nodes, one at a distance of 2, 2 at a distance of 4. So 4 is the maximum. In the right subtree, what is the maximum distance? 4. So 4 plus 4 plus 1, that is 9, right? So we get like this, right? We get the maximum diameter like this. So same thing we'll do for n-ary tree, but for n-ary tree we do not have 2 nodes, we have n nodes for like n child nodes. So we have to find the first maximum and second maximum because it will always diverge from there, right? It will go from one end to the other end. So we just want 2 child nodes, so we'll take the first max and the second max. So does it make sense? Does it make sense to everyone? How is this working? Does it make sense? Okay. Is it clear with everyone? Let me know if you have any doubts with the logic. Any doubts with the logic or something? Pretty simple question as well, this one. The return value of max site in diameter should be answer equals to max site root. The return value of max site in diameter should be max site leaf. You are telling that it should be answer equals to. That's not the value thing, right? Answer equals to, if I do this, it will give me what is the maximum distance or maximum depth of a leaf node from root. That's not what that's not something that we want, right? We want what is the maximum diameter. So this is just a helper method that returns the maximum distance of a leaf. So we find that so that we can get the left max and right max here and then find the diameter like this. Time complexity, yes, order of n. Time complexity is order of n. So we are just doing a simple DFS here, right? Nothing else. So we are just doing a simple DFS here. So that's order of n. Uh, yes. So yes, we are actually finding what is the maximum height, right? So it's just a simple DFS, right? If you look into this code, it is just DFS. It is nothing but a simple DFS. So and the left, we are DFSing on the left subtree, we are DFSing on the right subtree. So that's why it is order of n. Everything else is order of one, right? Everything else is order of one. So it's simple DFS. All right. Yes. So time for homework. We are done with the class for the day. So this time the homework will be a bit difficult. There will be easy problems. There will be difficult problems as well. So first is, it's a basic problem. You have to do the in-order traversal on a tree. So if you don't know what an in-order traversal is, you read it up, right, and do a in-order traversal. So it's basically DFS on the right, left subtree. Then you visit the current node. Then DFS on the right. So the answer will be 312, right? Then return answer will always return 0. Why will it return 0? We are updating the answer here like this, right? We are updating the answer here with the diameter. So we are finding the diameter across all the nodes, right? We are finding the diameter across all the nodes and we are updating the answer here. So it will not return 0. So this method is different, right? This method just finds the maximum distance of a leaf node in the subtree of the given node, right? But we just don't want the maximum distance of a leaf node. We want the distance between two maximum distance leaf nodes that are passing through. Passing through. Yes, exactly. So answer is a global variable, and we are using it here. Not a global variable; it's a class level variable. Yes. Okay. So this is simple. Second is also easy. You have to convert a tree into mirror. So basically, you just have to rotate the left and right child nodes. So this is also pretty simple. It's a easy problem. The third and the fourth problem will be difficult. So uh, the third problem is you have to find the maximum path sum between two leaf nodes. So you are given two leaf nodes. You have to find the maximum path sum between them. It's not a diameter anymore. It's like each of them has some value. So between two leaf nodes, what is the maximum path sum, right? So for example, between these two leaf nodes 4 and 5, it will be the maximum 4 4 8, then 9 10 11 and plus 5 16. Yes. So that will be the maximum path sum, right? So that this is a difficult problem. Try solving it as well. And so fourth is boundary level traversal. It's you have to find the boundary level traversal. Left boundary nodes defined as the path from the root to the leftmost node, and reverse right boundary nodes, and something like that, right? So the answer will be 1 2 4 8 9 6 7 3. So basically it's traversing like this: 1 2 8 9 6 7 3, like this. So if you see into this diagram, this is, so you have to do a boundary level traversal the tree, right? So for this it will be 1 2 4 6 5 7 8 3 9 something, 7 8 3 7 8. So you have to do a boundary level traversal, right? So this is the last problem. Try these questions. You have a few days, like you have the weekend, entire weekend. So try using that. That's why I have given difficult problems for the day, for today, because you have the weekend. So try solving these. The questions again, you will get them in the description. So make sure you check it out. All right. Okay, so that's all I had to discuss for the day. So thank you guys for joining in, and I'll be seeing you on the next day. Make sure to do the homework as well. The problems are really nice, so try solving them.